You're welcome to yet another of a series of lectures in inorganic chemistry. Today we want to look at the chemistry of gallium, indium, and thallium. Gallium, indium, and thallium belong to the same group with aluminum and boron. But for the purposes of this class, we will not consider these two. We will consider gallium, indium, and thallium because of the peculiarity in their reaction. But before we start, as it is conventional in the study of chemistry, we will look at the electronic configuration, the way the electrons of gallium, indium, and thallium are arranged. You realize that gallium will take the argon core, argon 18, having its 3p6, argon 18. Immediately after which, the 4s orbital comes in, and the 3d before the 4p1. So conventionally, as you do know, this is not part of the valence orbital of gallium. When we are considering the valence orbital of gallium, we are talking about the 4s2 and the 4p1. Same applies to indium. Indium will take the krypton core, 36, showing its 4p6 field orbitals. As it shows its 4p6 orbital, indium will bring in the 4s, the 5s, the 4d, and the 3 and the 5p1, as you can see. And like we mentioned earlier, the D does not assume any part here. So when we are talking about the valence orbital of indium, we are referring to the 5s to 5p1. But when we get down to thallium, the difference is more remarkable. There's a slight variation when we consider thallium. Thallium has gone down, as you can see, he has gone down to the sixth quantum state. The sixth quantum state. For which reason, therefore, you agree with me, if you go back to your elementary chemistry, you remember that we have the 2, 8, 8, 18, 18, 32. The 2 here, talking of S, 8, S and P, 8, S and P, 18, S, P, D, 18, S, S, P, D, and F, S, P, D, S, P, D. But when you come to talking about 14 in 32, you talk of S, P, D, and F. sure you know S is 2, P is 6, D is 10, and F is 14. That's where we got the 2, 8, 8, 18, 18, 32. So this is the first 18, the second 18, and the first 32. The first 32, we take charge of 18 plus 14. That's how we got there. So in this instance, xenon will give its 54 electron core. When it gives its 54 electron core, you go to xenon there, you see him in 5p6. Sooner after which, the 6s2 will come in before the 4f, 3d, 5d10, before you now have your 6p1. And like we said earlier, this, and this do not come in when we are discussing valence orbital. So the valence orbital of thallium will become 6s2, 6p1. That is where we are. So generally, you can say that they have the ns2 np1 valence orbital. ns2 np1 valence orbital. We move ahead to see their occurrence. You move ahead to see their occurrence. You realize that gallium, indium, and thallium, as in the three, gallium and indium are stable in air. They are stable in air. They do not readily react with moisture. Gallium and indium, gallium and indium do not readily react with moisture. They are stable in the atmosphere. The atmospheric moisture in the air do not readily attack gallium and indium, except there is excess oxygen. Except in the presence of excess oxygen. Gallium and indium are stable in air. The moisture in the atmosphere does not readily attack gallium and indium. Thallium, on the other hand, reacts. Its surface tarnishes. The surface of thallium tarnishes in the atmosphere. It undergoes oxidation in air. So there is surface reaction of thallium as against gallium and indium that does not react with moisture. The three, gallium, indium, and thallium, react with mineral acid. to give off hydrogen gas. The three, gallium, indium, and thallium, react with mineral acid to give off hydrogen gas, particularly HCl and H2SO4. The three congeners, the three, gallium, indium, and thallium, react with mineral acid to yield their respective salts and give off hydrogen. But the difference is clear when you are talking thallium. Thallium will react, but it will react much more slowly than gallium and indium. Reason being that the salt formed by thallium salt that is formed when thallium reacts with this acids is soluble, and when the salt dissolves, it will set back ions into the medium. So the reaction of thallium is slightly slower than the reaction of gallium and indium. Gallium is amphoteric in nature. That is to say, it reacts with both acid and bases. So gallium suffers instantaneous reaction with sodium hydroxide. Instantaneous with sodium hydroxide to give off hydrogen, just as when it was reacting with an acid. So we say that gallium is amphoteric. Meanwhile, indium and thallium are basic. They are hydroxide and oxide are basic in nature. Both indium oxide and thallium oxide are basic. Their hydroxide and oxide are basic against the amphoteric nature of gallium. We would see that as we come down from gallium to indium to thallium, that gallium will be prone to covalency, while thallium will be prone to electrovalency. We want to explain. From this electronic configuration, you see that the s electrons are paired up. They come in pairs, are paired up. In conventional discussion, we say that the s electrons are to react first before the p. But in this chemistry, that is not the case. That is not the case. The S is paired, and for the S to react, it needs to unpair. It needs to unpair. The paired electron in the s orbital must first of all undergo unpairing. Unpairing. That is to say, the up and down of the s must unpair to give the up and up. When it unpairs, that is when it would be possible for one to be lost. So, the peculiarity of the chemistry of gallium, indium, and thallium is that the coming in between of the lower orbitals, the coming in between of the lower orbitals tend to exert a dragging, attracting force on the valence orbital electrons. And when they exert this dragging tendency, they tend to hold the valence electron stronger as you are coming down. As you are coming down from boron, as you are coming down, the coming in between of the lower quantum states tend to constrict, lower the atomic radius. And as it lowers the atomic radius, it draws the valence electron closer to the nucleus. Therefore, the effect of the proton inside the nucleus will be greater because the atomic radius is smaller. For this reason, this element tend towards covalency. Apart from this constriction, the pairing of the s orbital, electron predispose the p to react. So, that phenomenon whereby p react instead of s, we refer to that phenomenon as inert pair effect. Inert pair effect. That is to say, the pairing of the s electron, which requires extra energy to unpair before acquiring ionization energy, predispose the p to react in place of the s. And we call that inert pair effect. By this, you realize that thallium will be more ionic. Thallium all of them are supposed to be, the three of them are supposed to be 3+, but that is not the case. They are more stable in M+. Thallium in particular is more stable in +1 state than +3, even though they have 3 valence electrons. This can be seen when thallium reacts with chlorine. As thallium reacts with chlorine, you find out that thallium react with chlorine, you find out that thallium is more ionic, is more ionic than thallium Cl3, is more ionic. What we're saying here is thallium Cl is more ionic than thallium Cl3 covalent. What do we mean there? It will be more difficult. It will be more difficult. It will be more difficult to lose 3 if this is your thallium and these are the 3 electrons. He will readily lose 1 in the first ionization energy, and before the coming in of the second ionization energy, you have thallium plus there for him to form thallium 2+. This ionization energy is far greater than this. And the same applies in thallium 3+, which is also far greater. So for that reason, thallium Cl3 will tend towards covalency. The same applies when we talk of gallium. When we talk of gallium, the same applies when we talk of gallium. The same applies when we talk of gallium. Gallium will form gallium, but this is more covalent than thallium Cl. It is possible, as you would see, for there to be dimerization in gallium. Gallium Cl3 will rather exist as gallium 2Cl6 with the 2-. Let's show what we mean by dimerization. What do we mean by dimerization? This is it. This is what we mean. The structural representation of that will be gallium 1, 2, 3, 1, 2, 3, Cl, Cl, and 2-. So there is this bond formed here. There's that bond formed there, which shows dimerization, which is a covalent property. Now, in another of our comparative chemistry, we see that thallium in its plus one state, thallium in its plus one state, bears semblance with silver 2 in her plus one state. How do we say this? Thallium chloride tarnishes upon exposure to sunlight, just like silver will do. Just like silver will do. But the difference is clear that upon heating thallium hydroxide, it undergoes a reaction to yield thallium 2 oxide upon heating. That is the marked difference. The similarity between the two is when you compare their photosensitive or reaction in the presence of sunlight, that they will undergo color change. But when thallium hydroxide is being heated, it will rather transform into forming thallium oxide. With this, we can refer you to our PDF page in Google, and the PDF in Google Drive. At the end, when we shall post this clip, we will put the PDF link that you can use to obtain the PDF file. You are also free to go to the comment section and ask your questions. We will attend to your questions as we see them. Thank you very much.